Hi. So this project is about laptop price prediction. The su- the project title is very simple, but when you look at the project, it's a really very good project for a data science aspirant, because this project involves a lot of pre-processing and exploratory data analysis. There's a saying that if you are giving a very pre-processed and good data to even a slow algorithm, the slow algorithm will also give you better results. So that kind of analogy is being discussed in this project. So the exploratory data analysis part of this project is very important, and it requires and if anyone does it from end to end, he or she will get a very good knowledge about EDA and will get a very strong base on data science, especially supervised learning. So let's look at what this project is. As the name suggests, it predicts the price of the laptop based on several features. Let's first look at the workflow. So workflow is similar to any other end-to-end full stack data science supervised learning project. That is, we load the data into the pandas data frame, then we do EDA, then we do model building where we select the algorithm for prediction, and then we do hyperparameter tuning of that algorithm, and then we save the model into a pickle file, and then we unpickle the file into an UI and integrate our machine learning model with the UI, and then we deploy our entire code on Heroku cloud. A very simple, straightforward workflow of a full stack data science project. So let's see at the working demo of this. So the working demo goes something like this. Let me select the brand to be HP and let it be notebook. I'll select 8 GB RAM, operating system as Windows, weight of the laptop, let it be 1.37 kilograms. I don't like touchscreen laptops. There's no IPS. Screen size, let it be 100.45 inches. Screen resolution is 1920 into 1080, and this is, let me say, i7, and let the HDD be 1024, that is 1024 GB. That should be actually TB. I'll change it. SDT is 256, and yeah, 1024 GB is 1 TB only. It's right. So Intel is GPU is NVIDIA. So let's try to predict what the price comes out to be. Yep, the price comes out to be nearly 51,000 to 53251. We get the same kind of result when we see on Amazon or Flipkart. 8 GB RAM, a standard 8 GB RAM, Windows OS. It has a NVIDIA GPU. It has normal weight and screen resolution and Intel iCore i7. Because of the weight, I think weight is a little bit less, and screen size is also a little bit less. Due to that reason, I think the price got reduced a little bit, but this is almost in the price range. I think so price range would be from 50,000 to 57,000, but this predicted good basically. In order to get exact results, we need to get a lot of data for it, and again, you will understand why this is giving you almost 80% accurate result. It's all because of pre-processing the data very goodly, right? So in this project, pre-processing of data plays a very vital role, and yep, looking forward for the pre-processing steps. So in the last video we saw the overview of the project and how the project was working in a Streamlit application. So now we will get started with the project workflow. All the steps which were mentioned in the project workflow will get started one by one. So the first thing is we would require all these dependencies, basic dependencies in all machine learning and data science projects. That is, import pandas as PD. This is for panel data, or you can say data frames or series. Import numpy as np, that is for numerical processing, and then cbon and matplotlib for data visualization. So just simply hit shift enter. This gets imported. If you don't have these dependencies, then simply you just need to do pip install, just this command, pip install, and then the package name, let's say pandas. So pip install pandas and then shift enter. That's it. So that will get installed. For any library, you have to do it in that way. Then we would read the laptop data.csv file, which is present in the same directory. So df is equals to pd.read csv, and here we get the data file, company, type name, inches, screen resolution, CPU, RAM, memory, GPU, operating system, weight, and price. So we will be predicting the price variable, price column here based on all these attributes. We see that unnamed 0 is not required, so we will be dropping it. And then as we can see that removing the unnamed column, that is now we see that we have dropped the unnamed column, and then we are having the required features. Then we will check for null value, whether the data frame is having any null value or not. We see that there is no null value present. We will see if there are any duplicated rows, and we find that yeah, there are 29 duplicate rows in the data frame. Let it be for a while, and let's see ahead. Let's go ahead and see. If we click on df.info, we see that there are almost 13,003 entries, that is 13,003 rows, and there are 10 columns, in which 10th column is what we want to predict. So they are almost like 9 trailing columns. Yeah, so now once we do this basic checks, everything seems good. Then we will separate the categorical features and numerical features. So this is the command, data frame.select data types, include all the categorical features. So wherever we have object in the sense object means categorical features, and we want the column names of them. We don't want the entire data, we want just the column names. So in the numerical values we do the same. We say int 32, int 64, float 32, and float 64. We want all the integers and floating point columns, and then we hit shift enter and we get this as an index. And then this function is all about unique values which are present in the in a particular column, and then the value count of the particular column. So for column in df.columns, I'm calling the unique values which is present in every particular column. And then if I hit shift enter here, so I see that the details of particular column company. So the company column is having these many laptops, like unique laptops like Apple, HP, Asus, Dell, Lenovo, MSI, Microsoft, Toshiba, Huawei, and all. And then the type name, the laptop type name, like the model of the laptop, like ultrabook, notebook, netbook, gaming laptop, 2-in-1 convertible workstation, etc, etc. Details of the inches, how much long the laptop is all about, and everything. So the resolution, and yep, now you can see over here the columns: screen resolution, CPU and GPU, CPU and memory and GPU. You can see this is all text data. We need to do a lot of pre-processing over here in order to get good results. So we have to convert a lot of this. So that is why in the introduction I said there is a lot of requirement of pre-processing in it. So we will be following the same. Okay, so let's see these upcoming in the next video. Alright, so in the last video we just saw we declared two functions, unique values and value counts, and we just saw how their unique values are differing, and we have a lot of text data which we need to process, and we have to work a lot on the data pre-processing. We got an idea about it. So while observing the CPU column and RAM column, so I just made few kind of observations here. So in observation we can see that if we remove GB from RAM, I can make it as an integer value. Then after now goes with memory as well as weight. So the same goes with the memory as well as weight. So over here what do I mean is in this 8 GB, if I remove this GB and I just take 8 and I make a drop down of it, it becomes the numeric value, right? So the main aim is to remove this GB from this 8 GB. So we'll be doing it. So how to do it? So we say df ram is equals to df ram dot str dot replace string dot replace. First, our main intention is if you are having 8 GB, so first we will replace this GB with a white space. So when it's with white space, what happens? It becomes something like this. See over here, it becomes something like this. If this is the case, and then I remove a white space, so it becomes 8 and then space. Then what I need to do is the same kind of thing I will do it with weight also. So in weight, if we go and see weight, so in weight also we have some kilograms and all those things, right? So yeah, so in weight column also, if we just browse, we will get some kgs, and yeah, over here, so we get the kg and kg. So we have to remove those kgs with a space. So that's what these two lines are doing, and then we will convert this into an integer value. So for doing that, we use the as type function, which is there already in pandas. So yep, that is all this cell is doing. It's just converting this into numeric value. The categorical value of ram and weight has been converted to numeric value. So that's what has been done over here. See, we see 8 and weight becomes 1.37. So kg and everything is gone. And then we do df.info. Our main aim was to check about weight and ram. So it became floating points and integer points. Great. So now moving ahead to the most important part of this, this was all about a little bit of pre-processing. Now comes the main thing, that is EDA, which I was talking about. So EDA, so first we will see the distribution plot of the our dependent feature, that is price. So the price looks something like this. So if we see the distribution of this is a little bit of a left skewed Gaussian distribution. So I feel this is centrally distributed. I feel this is left skewed a little bit, not completely. Let's see how the other features and things be. So plotting the counter plots of categorical variables. So in the category we have 3 or 4 categorical variables here, that is company, type name, RAM, operating system. So we'll be using cbond to plot them. Okay, so I have defined a function over here named as draw plot, which takes in the column name. So I have defined a figure size, object, and sn.count plot, df of call, and palette is plasma, and then plt.xsticks. I want my x labels to be vertical, so that is why I have kept this plt.xsticks rotation equals to vertical, and these categorical columns I want to explore. So for column in this categorical variables, I will call the function here draw plot, and we see the results here. So we see that company and their counts. So we see that HP has almost like 275 laptops. 275 laptops are almost of HP out of 1303, and Dell has almost crossed more than HP. That's almost like 290 or 285 laptops. Same goes with Lenovo. We see that the least is with Google and LG and Fitsuji, Samsung, Vero. You can just go around with this little bit of statistics on your own. And then we have the type name, that is what kind of models are mostly sold. So we see that notebook model are mostly sold. We have the Lenovo notebook, HP notebook, Apple notebook. So notebooks are very popular in the market, in the laptop market. So it's almost like 725 and more. So this counter plots give you a very good insights about the categorical variables. So I highly recommend counter plots for categorical variables. You get a lot of insight out of it. Then we will see average price for each laptop brands. This will say as the insight that as per company, the price of laptop, how the price of laptop varies. So over here, if we just plot a bar plot over here, this gives us the inflation of the company and the price of the laptop. So basically what I mean to say is, over here, if we consider this HP laptop, this tick is, you are seeing this tick, right? The above value is almost near to 65,000 mostly. So it's saying that the maximum price of an HP laptop can go up till 65,000 or more than that, maybe like 70,000. Maybe the data is not given here, which maybe there are few laptops which go up to like 1 lakh also in HP, but those models have not been released in some parts of countries, or maybe that part is not available in the data set. But according to the data set, HP laptops, the maximum price comes out to be 65,000 or more than, or like in between 60 to 70,000, and the minimum price is almost like 52,000 or 50,000. So this, the below tick says as the minimum, and this one says as the maximum. Okay, or we can say that the average also, not minimum, sorry, we can say that the average selling price, right? So Apple, if we see Apple MacBook and everything, they go more than 1 lakh, and minimum would be, and like average selling would be something near to 67,000 or 75,000, like that. Okay, we can see a lot of variation in the price in this way. So like we get to know what is the average variation of a company's laptop and what is the maximum price which a company can assign to its laptop. Got it? So if we see one Google laptop, if we see, just see this Google laptop. In the count plot of Google, if we see, Google just produces almost like 5 or 10 laptops, mostly 10 laptops, at most 10 laptops, and just see the variation in price in Google. Those laptops are more than, like, the maximum price of laptop is almost crossing 1 lakh. So you can see this part is a very varying factor in this. So yeah, this kind of bar plots also help us to understand the variation of company and their laptops. Then we see various types of laptops. We see that notebook is something like 700. These also we just saw over here. And let me just execute this. So we get the same plot, and yeah, laptop type and variation about the price. So laptop type and variation about the price. Here we saw the laptop company name and then the variation in price. Here we are seeing the type of the laptop. Type of the laptop in the sense ultrabook, notebook, gaming laptop, 2-in-1 convertible, and workstation, all those kind. So we find over here that notebook, which is most popularly, like many of the people use notebook model very much. You see a very small tick over here, right? The reason is because this is a general purpose. The people use mostly notebook, and then the price variation must not be that much in this. The price must be reasonable so that this notebook product must grow in scale. Okay, so there's something in business analytics that if there are so many people who are purchasing, or the demand of a particular product is so much, like notebook is so much, you have to maintain a reasonable price for it. So that is the reason why you can see a very small tick over here, not too high, not too low. Whereas if you see in Google laptop over here, this gives a very good insight. Like there are very less number of laptops in one dataset of Google, but just see the variation of price. It's almost starting from 60,000 and it's varying till 1 lakh or 1 lakh or above. 10 laptops starting, minimum start is 60,000, and maximum it can go till more than 1 lakh. So a lot of variation in price because of the brand Google. Okay, so we see over here in workstation also, we can see the same kind of thing. Workstation also, not many people buy workstation laptops. These workstation laptops are almost bought by people who do very high-end tasks, like they need a lot of computational power. So it's, the count is almost like 10 or 20, maybe 20. So you can see the variation in it. So when the count is less and the effect of price and this thing is more, these attributes give a lot of insight in your data science project, right? You have to not forget this, and you have to not forget to exclude them. Maybe some people, they exclude them because they are not giving some part of it, but no, they are a very important part and they can give a lot of contribution too. So these kind of plots, like comparing the dependent variable which each of the dependent with each of the independent variable, will give you a very good insight. Okay, then we'll go ahead and see the variation of inches towards the price. Scatter plot would do a good thing over here. So on y-axis is this and on x-axis is this. We see that 17 inches laptop, or almost like 17.5% inches laptop, they are more than, like, the price has reached more than 3 lakh also sometimes, and most of the public buys the laptop around 13 to 14 inches. We can see the crowd over here, the scatter over here. So most of the people buy around this, and that makes sense because we almost buy like nearly to 15 inches, mostly till 15 and a half. It depends from user to user, but most of the public buys in that range, and the data shows it right. Okay, so these were some basic plots, and how the price and everything inflates the, how every attribute is inflating the price. We saw it, and in the next video we'll look more into these insights. Thank you. Alright, so in the previous video we saw how these kind of variables like these kind of variables like type name, company name, and the what we say inches, all these attributes, how they are contributing towards the price, like what is kind of variation between them, what kind of variation is shown in inches and prices and type name and them and all. So let's now look more deeper and then see for text processing things. As in the previous videos I said that there is a lot of text which needs to be processed. Over here we see that screen resolution, GPU, and memory, this needs to get processed, right? So we will be looking into the processing steps now. So yeah, so over here we'll be looking at the screen resolution value counts. Let's see what is the value count here. We find that full HD laptops 1920 into 1080 are 507, 1366 into 7868 is this, IPS full panel is this, and there are many more varieties of screen resolutions which are available. You can just use this value counts, and if you want to make it in a good way, you can store the counts into a histogram. You store this counts into a list and then plot a bar plot for getting insights, but this works fine, it's not an issue. Yeah, so now we will be creating another column named as touchscreen, whether the laptop is a touchscreen laptop or not. So how to do that? So basically, if you just observe in this, we are having a touchscreen text over here, right? Touchscreen, 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 touchscreen. So what my analogy over here is, don't go to break the entire text at once. Break it side by side. Here you see two important things. One is IPS panel and one is touchscreen, and one is full HD, ultra HD, HD. You can ignore HD because almost everything is HD. The important part is about IPS panel, that is IPS and touchscreen. This is the most important thing. So we will be making another column here, that is df of touchscreen, which is equal to df of screen resolution dot apply. So we are applying a kind of text processing here. Lambda element 1 if touchscreen in element L0. What does this mean is, this is a very short technique to write a loop kind of thing. In JavaScript this is known as a for each loop. In Python also we have a for each loop, but if we want to make a one-liner, so we use this lambda function. So what this lambda function is saying is, element for if touchscreen in element else 0. So if you just type in df of screen resolution, you get a series of things. For example, I'll show you. If you just type in df of screen resolution, you get a series, right? You get this series. Okay, so now what we are doing is in this series from 0 to 32, we are applying a lambda function. Lambda function will go one by one over here. So from 0, from 1, then for 2, then for 3, then for 4, then for 5. It's kind of like a loop only. Okay, so element, so lambda takes in an object which is this element, and it's saying that 1. Okay, what 1? So the control flows over here. If touchscreen is an element, so the element is what? IPS panel retina display 2560 into 1600 is our element. So it's saying that the lambda function will return 1 if touchscreen is present in this element. Is touchscreen present in this element? No, it is not. So that is why it is giving us 0. You can see. Is touchscreen present at? So wherever touchscreen is present, there it will be 1. See over here, if we just see 1298 row, we will get. Okay, if we just see 1298 row, if we just kind of execute this, and if we see df.tail, we will see over here touchscreen. We get touchscreen because there is touchscreen written here, right? So if we are having a touchscreen mentioned in our text, then we say 1, else we say 0. So that kind of column was made, and sample is just it will randomly select some column, it will randomly select some rows from your data frame and display it. And here we have a count plot, sn.count plot of touchscreen. So we will come to know how many laptops are touchscreen and how many are not. So we see that almost like 190 laptops are touchscreen, and rest all of the laptops are not touchscreen. So this is also very important. Yep. Now touchscreen in comparison to the price of the laptop. Again, as we made a new feature which is touchscreen, now we will compare how this touchscreen feature is inflating the price. So we see that most of the touchscreen laptops, the highest price is more than 80,000, and the minimum price, or kind of average price, is like 70,000. So whenever a laptop is a touchscreen, maybe you can get it in 65,000. Okay, it can vary from 65,000 to 70,000 on average, but it can go more than 80,000 on max. So that is what this plot is showing all about. And without touchscreen, as I showed you this kind of plot, where this kind of plot, where the demand of this thing is very more and price has to be reasonable. That kind of thing is shown again over here. See, that kind of tick is shown again over here. So, and the price limit was also the same. Yep. So these plots are also very important. Yeah. So as mentioned earlier, that we are looking for IPS panel, which are important features, and touchscreen, which are important features. So we dealt with touchscreen. We saw how touchscreen inflates the price. Now it's time for IPS. Is IPS panel available on the laptop or not? So the same kind of function, same kind of logic we are writing, which we wrote over in the lambda function, lambda element 1, if IPS in element, else 0. And then sampling. We see that wherever there is IPS panel, there it is 1, else it is 0. As simple as that. Let's see the count plot of it. We see that like 300 laptops, mostly like 350 laptops are having IPS panels, and rest all are not having. We see the variation of IPS. Okay, over here I did the same thing, right? So I have to take IPS here, right? Yeah. So if we see the inflation rate, it is the maximum price is hitting almost like 80,000, not more than that. The maximum price is hitting almost like 80,000, not more than that, and the average price is in between 70 to 75,000 over here. Okay, so we are done with touchscreen and IPS now. So we have completely passed the text of the screen resolution. Now we will move forward for separating the X resolution and Y resolution of the screen resolution. we saw some kind of numbers here, right? Like 2400 into 1600, 1920 into 1080, 3200 into 1800, 2560 into 1400. Almost like every attribute over here has numbers, so we need to extract these numbers. These numbers will be extracted in the next video. So in the previous video we just extracted the IPS and the laptops which are having touchscreen, and we saw how touchscreen and IPS give a variation in the price of the laptop. Okay, so now we will try to extract the resolution. So for that, extracting the X resolution and Y resolution, we will split the text at X and then separate the two parts. What do I mean by that? If we just have a look over here, we will separate the text at this. So if we just look in a sample resolution, what a sample resolution looks like normally, a sample resolution looks something like this, right? Over here. So if we want to split them in two parts, what would we do? We would say before X some part, before X some part is there, and after X some part is there, right? So before X what part is there? 2560, and after X what part is there? 1400. So we will be splitting in that way. Okay, so that's what is said over here. Split at X, n is equals to 1, expand is equals to 2. Expand is equals to 2 in the sense means whatever is there in before 2560 also take that into consideration, even if it's a blank space. So if we see over here, before 2560 everything is considered, even blank space is also considered, full HD, everything, right? Got it. So now this kind, so we will execute this. So we will get a split df, then we will say split df is equals to df of screen resolution dot split of this thing, and df of X resolution is equals to split df of this thing and that thing. That was just for a sample, and now we get X resolution and Y resolution. This thing is just replicated over here, just the name of the column is changed, that's it. This is nothing but to just to see if this is working or not, that's it. Okay, so over here if we execute this, we get the X resolution and Y resolution now. So basically from the whole text of X resolution column we need to extract digits from it, but the problem is number are scattered in some cases. The reason why I'm using regex is this will exactly get the numbers what we are looking for. So regular expressions are a very powerful tool when we want to extract some kind of numbers or characters or special symbols from a very huge chunk of text. And I must say that regular expressions form a base for natural language processing. Regular expressions are heavily used there, and they are widely used wherever there is a textual data. So here also we see that we need to extract numbers. So from this we need to extract numbers, right? So we don't know the exact position of the number. So for that the reason we are using regular expressions. So over here, what does this mean is just look at the regular expression what we are saying. First we replace all the commas with spaces. So so in the data frame, if you explore the data frame a little bit, we find that there are few columns, a few rows or tuples which are having commas. So we have to replace those commas with what we say some space, and then we will find all the text rows which are satisfying this kind of regular expression. So what is this regular expression all about? Now over here we see that /d plus dot question mark /d plus. Now /d means that is the integer number, okay, and slash dot question mark means all the numbers which come after a number, and /d plus the string must end with a number. Got it? So if we consider this kind of text over here, IPS panel display, let's say that we consider this text and we paste it over here. So we see that now if we try to match this, Okay, so what we will be matching here is, we will be first looking for the number. So where we are getting the number, we are not getting any number, we are not having any like commas or anything. So this will get this will get passed, no problem. Then over here we will see that we found a number over here, that is this, and we will see if there is any dot or not. There is no dot. Okay, then at the end also, is the end having a number? Yes, this is only the end. This part is the starting and this part is the end. That is also a number only. So we will extract this, right? So that is the thing which we have applied here. So this is a regular expression. Maybe you maybe there might be little bit of confusion. So what do I suggest is, you take some sample rows and try to use them exactly by using this regular expression, and see on some samples, and then better you'll get an understanding of it. Okay, so once we get the X resolution and Y resolution extracted, the next thing is we need to convert it into integers. They are not integers, they're text. Basically, we applied regular expression on text. We didn't convert those things into integers. We need to convert them. So this code does that. So let me execute this. I got X res and Y res, and then let me execute this as well. So we see that X res and Y res is now integer. Now let's look at the correlation map. Over here we see a lot of correlation among X resolution and Y resolution, and that is true because X resolution and Y resolution are almost like very close to each other also. That's not an issue. We'll see how to manage that in a while. Okay, let's see the correlation of features with price. We see that RAM gives a very good correlation. RAM is a good correlation. X resolution and Y resolution, like the resolution of the laptop, that is the screen size, like 1920 into 1080, full HD laptop, ultra F4 HD laptop, 4D laptop, all those things, they come under resolution. So we see that almost like 55% is affected. The price variable is affected almost like 55% with the resolution only, and we see that the 74% of the data has been affected with the the RAM. So RAM, and from this correlation we can say that resolution and RAM are very, very important features. We cannot remove them, right? So that is what I have written over here. Now what we need to do is, even though X resolution and Y resolution, they are very important, we see a little bit of pattern over here. We see that this is like 55 and 55, right? Maybe kind of they might be under a clash. Got it? So we have to remove it. So this might be a case of multicollinearity, when multicollinearity is a situation where more than two features are contributing the same kind of thing. Then that may affect the overall outcome. That must not happen. So what we will do is, we will combine these two things, and we will create a new feature out of it. Simply some persons drop any one of them, but as in laptops there is something known as pixels per inch, so we will create that feature using the X resolution and Y resolution, and there is a formula for it as well. So X resolution and Y resolution, the pixels per inch formula is X resolution square plus Y resolution square by the total number of inches. We have the total number of inches column, we have X resolution also, we have Y resolution also. Why not, instead of deleting any one of them, why not use both of them and create a new feature, right? It may be a good suggestion. So we are doing the same thing here. So we are creating the same simple kind of formula. The same formula has been translated into code over here. This is nothing but X resolution square, this is nothing but Y resolution square, star 0.5 is nothing but square root of X resolution square plus Y resolution square, and the entire thing is divided by inches. And inches, it was a string, we convert it into a float. So that is why df of inches dot as type of float. And then when we shift enter and see, we got a pixels per inch thing over here. So and then if we just try to see the correlation here, yeah, this is see x resolution and y resolution. Using x resolution, y resolution and inches, this was already low, these two were very high and were battling against each other. So we combined all the three and we made a very good feature named as PPA, and that is contributing almost like 48% to the price. So now this has become a competitor with x resolution, y resolution and inches. And now as we made this feature PPI using this x resolution and y resolution, we can delete them because we got a very good feature instead of using this combination of three. So this is a kind of feature reduction by using a new addition of feature. So correlation analysis also plays a very vital role, and that is the reason I was saying in every video I am saying that exploratory data analysis and data pre-processing in this project is very important. You at every doorstep you'll get to see some kind of insights into this. So yeah, we saw that these two, so in this we saw that these three features could be combined and then we could make a new feature here. Okay, so we'll talk about more about pre-processing in the next videos coming up. So in the last video we saw how a combination of three features made a new feature, that is pixels per index, pixels per inch, sorry, and we saw that it is also giving a good correlation score with the our dependent feature, that is price. So here I have written the conclusion. As we observe that PPI is giving good correlation with the combination of three features, so we will drop inches, x resolution and y resolution as well. So yep, we will be dropping them because using these three features we made a new feature which is giving almost like 48%, like it's kind of giving 48% of its contribution towards price. So why we will drop it? So we will drop the unnecessary features. Now we will work on CPU column. So as that also has much text data, we need to process it efficiently as we may get good insights from them. So we are done with screen resolution here. Now we will start with CPU. So in the CPU column we see that we are having this kind of thing like Intel Core i5 7200U 2.5 gigahertz. So what we are basically interested in getting this i5 i7, what kind of processors do we have? We have mostly Intel Core i3, Intel Core i5, Intel Core Pentium, Intel Core i7, and maybe sometimes i9. Maybe in the latest features we have some i9 features, and then we have another company which is AMD Ryzen. We have Intel Pentium dual core, as we can see. Okay, so we are not interested basically in getting the 7200U 2.5 gigahertz and everything. We are not interested in it. We are just interested in getting this part. So over here I have written most common processors are made by Intel, right? So we will be clustering their processors into different categories like i5, i7 and other. So there we see that we have Intel Xeon, Intel Celeron, Intel Pentium, Intel Atom. But most commonly after 2010, almost every laptop which is produced by top MNC like Microsoft, HP, Acer, Dell, they are using either i3, i5, i7 or i9, not more than that. So that is why I cluster these kind of attributes like Xeon, Celeron, Atom into another category known as other, so that there are no more features. i5, i7, i3, i5, i7 are standard, but other than that also there are many features. Like, so I cannot just say that okay, if your processor is Xeon, if your processor is Celeron or Atom or Pentium or some XYZ, so if new feature comes on, then I have to keep adding that feature dynamically. So why not cluster them into some other category, because their presence is not that much in the market. So we will be using this kind of strategy. Now other means the processor of Intel, which yeah, so the same thing which I said. And the other category, the other company which makes processor is AMD. So we have to see about AMD as well. Okay, so over here what we will do is this thing is little bit tricky. So what we have to do over here is we will take this for example as a text. Okay, we will say that text is equals to this thing. Okay, and then we will say um, text dot split. Where we want to split, at spaces we want to split, just write split and then see, we get this Intel Core i5. So as in the now only I said that we are not interested in this part, we are just interested in this part. So we will use the slicing operator here. What we will do, we will slice up till third index, so that means it will take till second index only. So if I just shift enter, I get this list. Now what I will do, I will join the string, I will join this, right, dot join, I will join. So what do I get? I get Intel Core i5. I need some kind of space in between, so I will keep some space in between. So I got Intel Core i5. I got this Intel Core i5. So this is the main thing, right, over here. This is the main thing which I have written over here. Now, as I said about lambda function is an in-place for loop. So for example, in df of CPU, if you see, this is df of CPU. I'll just show you. This is df of CPU. If you just see df of CPU, this is a series, right? So in this series, what I want, this is a kind of a one-liner in Python, which separates all the characters and then joins what all characters are required. So this one-liner we just saw how it is working. So we are trying to integrate it to large scale in the sense, not only to this text. I want this kind of logic to work for all the column, all the rows which I am having. So for that I am using lambda function, lambda text. This means for every text in df of CPU, do this. I will again repeat, this lambda function means that for every text in df of CPU, apply this logic. What logic? This logic. We just saw this logic, right? Text is equals to Intel Core i5 7200U 2.5 GHz, and when I applied this logic, that is space dot join text dot split sliced in third index, I got a result as this. So this lambda function is saying the same thing. For df of CPU series, apply this logic so that I get a new column named as CPU name. So whatever result is coming, you just store it into df of CPU name. So we see that we get Intel Core i5, Intel Core i5, Intel Core i5, Intel Core i7, Intel Core this, right? So we get this. Now we'll move ahead. As mentioned earlier, if we go to Intel i3, i5, i7 versions, we will return them as it is. But if we get another processor, we will first check whether it is a variant of Intel or not. If it is a variant of Intel, we will assign a variable named as author to it. Else we will say it is an AMD processor. So we are having only two kind of processors here, AMD and Intel. So if a processor is a variant of Intel and specifically it is i3, i5, i7, we will say that okay, you go under the clutter of i3, i5, i7 respectively. If you are not a part of i3, i5, i7, but you are a part of Intel family, I am gonna consider you to be as other in Intel family. Got it? So the same thing is being done here. So I am defining a function here. So def preprocessor of text. If text is Intel Core i7 or Intel Core i5 or Intel Core i3, you simply return this only. No need to do any kind of thing. But if text.split of 0 is Intel, that means if we are having this kind of configuration or this kind of processor like Intel Atom, this doesn't belong to i3, i5, i7, but it belongs to Intel family. So that is why I did this. Else if text dot split of 0, this is the text. What is the text? Let's say that this is the text, and text dot split of 0 means what? If we try text dot split of 0, what we will get? If we try to do text dot split of 0 over here, what we will get? Okay, I'm sorry for that. Text dot split of 0. Oh, yeah, we will get Intel. So the same thing is done here. If it is Intel, then you return other Intel processor. So as per my logic which I discussed earlier, that if it is not in i3, i5, i7 category, but it is of Intel family, I am categorizing it as other. I don't want to make more features, I want to reduce my features into that way. Okay, but if that is also not the case, that means if the processor is not of Intel only, then return AMD only, AMD processor. Or specifically you can return other processor as well, no problem. Okay, but in the market mostly AMD processors, apart from Intel you have AMD only. So I just kept it as AMD. You can also keep some other name, or other also you can keep. To be more specific, you should keep other, but I kept AMD. It doesn't affect anything. So the same kind of logic. Now here, instead of writing one-liner function, I am calling this function. This function is almost like 12 to 20. This function is almost like 8 to 9 lines, right? This function is almost like 8 to 9 lines, so I have to use that. Okay, so yeah, I'll be using it, and then I'll be getting this text processor type text, and then I get this thing, right? Intel Core i5 and all. So I'll just pre-process it. Yup. So over here, CPU name, I get it as Intel Core i5 and i7. Let's just try to visualize it in a form of a count plot. It will be more clear. So yeah, we see that i5 is almost like 410, 420. i7 is almost like more than 500. The reason why i7 is more popular is because of the price inflation which we said, and then we have AMD processor, we have other Intel processors, we have Intel i3 processors. So we in total we have some 5 kind of processors. Okay, so let's see the variation also. Now the variation, we see that again i5 is mostly bought by public, so in the given range. i7 is not that much bought by the public, but you can understand that the reason of normal public prefers to purchase a laptop which is in budget like 40,000 to almost like touching a maximum of 63,000 or more, not more than 60,000 basically. So normal public will prefer to use i5 only. But if you are a very professional coder, or you play a lot of games and anything, so you require a very heavy laptop for it, so most of the people go for i7 processor there. And we see that even Intel iCore 3, like most of the common people who use laptops for business, and also they use i3 processor only, because they don't need any kind of software, just Excel works for them. Then we have AMD and other Intel processors. So this kind of relation also we can see in price versus processor variation. And then we will draw up the CPU column. And yes, we are now ready with our pre-processed CPU. So we processed screen resolution column, we processed the CPU column. Now we will head up to RAM column. Okay, so let's see about the exploratory data analysis of the RAM column in the next video. Till then, do practice the code. Next video we saw how we did the pre-processing of the CPU column, where we segregated the Intel iCore, i5, i3 and i7 processors into separate clusters, and other variants of Intel processors into a separate cluster named as other. And then we had another kind of processor which was named as AMD. So we also categorized processors which are not part of the Intel family to be part of AMD family. And then we said that not only AMD is possible, you can even write it as others. So we did the complete pre-processing of the CPU column, and we dropped the CPU column, and we saw how the price is getting inflated with the various kind of processors in market. Now we will head up on the RAM column. So we will see what kind of things does the RAM column provide. So we just see the count plot of RAM. We see that almost 600 or more than 600 people are using 8 GB RAM a laptop, and the other major quantity people are using 4 GB. We rarely find people who are using 12 GB or 6 GB. We find few people who are using 16 GB RAM as well. So let's see the bar plot and with respect to price. Here we see that the RAM is having a good relation with price, as we also saw in the correlation analysis that RAM was contributing almost like 74% to the price. So, and this bar graph is also stating that like as the RAM size is increasing, the price of the laptop is also increasing. A linear growth is clearly visible here, right? If you purchase a 64 GB RAM, obviously you will get more than 2 lakh rupees. The price of the laptop would be that. Okay, not even 64. If you try to purchase even 32 GB laptop, there are high chances that there is a particular laptop which is having more features additional to 32 GB RAM, and the total cost becomes more than 2 lakh also. So this is that, and the average cost would be nearly to 1,50,000. If you're using 32 GB RAM, that means that 1,50,000 is like an average price for 32 GB laptop. There's no kind of average given for 64 GB laptop, because there are no laptops in scale as per now in the market of 64 GB, or maybe the dataset doesn't has it. There may be many laptops which are in production, which didn't come or which are not released yet into the markets, but as per now in the dataset they are not that much. So maybe like 2 or 3 laptops are there which are using 64 GB RAM, but not more than that. So that is why there is no tick over here like this. And most of the common public use 4 GB and 8 GB, and we can see that that is almost like reasonable prices only, and everything is common here. So RAM column is very important. We cannot skip this column, as it is giving a good correlation also. Now about the memory column, so we will separate the type of the memory. So if we look at the memory column, so in the memory column what is happening is basically we see that we are having SSD, we are having HDD, and we are having a combination of SSD and HDD. So in few laptops, if you view on Amazon or Flipkart, they say that we are having 128 SSD and 1 TB HDD. We are having 256 SSD and 1 TB HDD. So there is a combination of SSD, HDD, and there are few laptops which use only SSD, and there are SSD, and there are few laptops which use only hard disk. So we are having 3 kind of things now, and there are few laptops which are using even flash storage, which is nowadays which has nowadays gained a lot of popularity, flash storage. And yeah, so there are many variants which we can see in this. So this is also a column which we need to pre-process a lot. So let's see the counts. So we have to do a lot of pre-processing here. So now we will apply the regular expressions as usual. So this expression will remove the decimal space. For example, 1.0 TB will become 1 TB. So a very simple regular expression which I have written here. So in memory column, convert this memory column into string. Maybe that is an object. It's better to convert into string, even though it is in string. It looks for you as a string. It's better to convert into string because you don't know when sometimes the things change. So it's better to convert into string. So we do as type as string, and then we replace all the decimal points or the digits which are coming after the decimal points with this. So this slash dot 0 means whatever is coming after the decimal, please truncate it. That means if it is 1.0 TB, it will become 1 TB. And regex equals to true means you do this for every column, sorry, every tuple which is present in this df of memory column. Okay, so once we get this done, next what we want is, we want to replace the GB word with this. So basically what we did is, there are few columns where we are having 1. See over here, I was saying about this 1.00 TB, 1.00 TB. So there were few columns which we noticed, and to overcome this only we did this line, the fifth line. To overcome those kind of rows only we did this, right? Now what we need to replace the GB word or TB word or SSD word. Mostly we need to replace this GB word, because this GB word is common everywhere, it is common. So we will replace this GB word with blank space. That is done in line number 9. And then this TB word will be replaced with 000, and it will be considered as GB only. So 1 TB is nothing but 1000 GB, right? So the same thing, that analogy, based on that analogy we are doing things. So if it is 1 TB, that means 1 and then TB. After TB we are truncating it, we are truncating the TB to 000, or we are replacing the TB with 000. That means 1000 GB. So we need to convert, we are maintaining a scale of gigabytes only, because most of our configuration is in gigabytes. So we want to keep that gigabytes as usual. So we are applying that kind of mechanism here. So if we find any kind of TB, we will replace it with 000. Now split the word across the plus character. Yeah, so there are few things, there are few places where we have plus characters as well. So this is a kind of a combination thing. So if you are having a configuration of 128 GB plus 1 TB HDD, so what this will do, first we will I'll just show you an example how the flow goes like. Okay, so this is 128 GB and 128 GB SSD plus 1 TB HDD. So the first line, that is this 8th line, what does this say? It says that after decimal, is there any decimal? There is no decimal, so this will be as it is only, no problem. Now what will happen? Now in the next line, that is line number 12. So in the line number 12, what will happen? They said that df of memory is equals to df of memory dot str dot replace GB with space. So this will get replaced like this, and this is space, and then SSD. Okay, and then we get 1 TB 1 TB HDD. After the line number 15, the result is something like this. Now, is there any TB? Yes, there is a TB. So we have to replace that TB with what? 0000 SSD plus 1 1 2 3 space HDD. So after line number 21, the string is looking something like this. Now what we are saying? We are saying that split the characters, split the string on plus. So if you split the string on plus, what will happen? We will get a list of characters like 128 SSD, comma 1000 HDD. We will get this list of characters, right? On the split we will get this characters. N is equals to 1, expand is equals to true. We discussed it. So that kind of mechanism is applied. And then what is happening? If we just do this, we get this kind of thing. So this is working fine. So now what we will do? We will strip up all the white spaces, basically eliminating all the white spaces. So df of first is equals to new df of 0. New df of 0 is this thing, and we are removing all the white spaces so that it becomes clean. And when we run this, we get this df of first. Then we apply changes. Yeah, so over here, what is this? So over here, as I said that when you are having HDD, SDD, hybrid and flash storage, these are 4 kinds of memory storages, right? So we have to apply some kind of pre-processing here. So what we did is, basically I'm trying to kind of make a boolean values over here so that it is easy for us to track, or it is easy for us to do ED on it. I'll just show you how it is. So I am making a list to apply as hard disk, HDD, hybrid and flash storage. Now for every value in list to apply changes. So what we are applying changes? df of layer 1 plus value df of first. df of first is this, dot apply lambda x1 if value in x, else 0. So if HDD is in value, what is value? Value is 128 SSD or 128 flash storage, 256 SSD, like that, right? I said that lambda functions are kind of one-liner for loops. Okay, so the same thing. So df of first has almost like 1303 values. So for each value you check if HDD is available or not. If it is available, then it is 1, else it is 0. First you do for HDD, then you go for SSD, then you go for hybrid, then you go for flash storage. So this loop runs that. This loop runs 4 times. This thing runs 4 times. So totally 4 into 4, 16 times this entire thing will run. Okay. So after the result, what we will get is, we will get 4 columns. Layer 1 HDD, layer 1 SSD, layer 1 hybrid, layer 1 flash storage. So what is the significance of this is, wherever only HDD is used, that system, that configuration is marked as 1. Wherever only SSD is used, that configuration is marked as 1. Wherever only hybrid is used, that is marked as 1. Wherever flash storage is used, that is marked as 1. So now exploratory data analysis of this will become easy. Okay, so yeah, so let's remove all the characters, just keep the numbers. So now we are interested in only numbers, right? So we will remove all the characters. So for removing all the characters, this is the command in regex /d, means only keep the numbers. Okay, remove all the characters, or wherever you are having characters, just replace it by space. It means the same thing. So if we do this, so we get it, and then next time we will do the same kind of processing for df of new df of 1. So new df of 1 will contain these kind of records. See why we are doing new df of 1, because there are few columns which are having plus also. We just considered till now we just considered laptops which are having HDD, only SSD, only hybrid and only flash storage. We have to now consider laptops which are having both. So to get the details of that, the details are present in new df of 1, right? So we have to create this column, new df of, that is second column. So in second column we have to apply the same kind of logic which we applied here. The same kind of logic which we did here is applied to the second column as well. There's no change. And then we will convert it into integers. So once everything is converted into integers, we are good to go. Now over here, this little bit of mathematical formula which is used. Okay, so this is like df of HDD is equals to df of first multiplied by df of layer 1 of HDD plus df of second star df of layer 2 of HDD. So what does this mean? Df of first is 128 star 0 plus 0 star 0. So this becomes entire 0 for the first row. So this kind of mathematical formulas are used, this kind of mathematical simple numerical this is simple arithmetic operation which I did just in order to reduce the kind of columns over here. So I see that layer 1 HDD, layer 1 SSD, layer 1 hybrid and all, they are so many columns. I just want them like HDD, SDD, hybrid and flash storage, nothing more than that. So for that reason I am using this. It's very simple, you can trace it. Then we will drop some unnecessary columns like first, second, layer 1, layer 2 and all. And when I do this, this gets executed correctly, and then when I sample, I get the pre-processed and kind of good data set looking like here. Okay, so yeah, so we can also look at the head part of it. I just took the sample. You can also look at the head part of it and get a good insight as well. And then we will drop the memory column because we have pre-processed it completely. And then we will see the correlation of now we see that SSD is giving good correlation, flash storage is giving none because there's almost nothing which gives a good correlation there. We see that SSD is giving a good correlation here. So we will talk about the correlation analysis of these memory columns in the next video. Till then, do practice and do revise the code here, because this is a very important part which I discussed. So in the last video we saw how we segregated the HDD, SDD, hybrid and flash storage memory storage devices or memory storage inputs into other categories like HDD, SDD, hybrid and flash storage, and we saw the correlation of each of them with the price. And we got an interesting pattern over here saying that hybrid and flash storage are kind of negligible here. HDD is giving a negative impact on price, and that is true because nowadays if we look at the configuration of laptops, HDD is slowly getting decreased day by day and SSD is getting increased more, because SSD provides a very good, it's very fast, and also it provides good services over HDD. So maybe many people are working on flash storage and SSD more than HDD. So based on the data we can see that HDD is having a kind of negative correlation. So whenever you see negative correlation, it's not like you have to delete it, you have to keep it, because it's providing some kind of bias to your providing some kind of, it's giving some kind of contribution towards a bias in your data set. And totally eliminating bias is also not good. You have to keep some kind of bias so that there is like low bias, low variance factor. Okay, do not eliminate the entire bias, otherwise the algorithm will not learn only anything. So we have to make sure that whenever we see negative things, we have to not remove it. They give a lot of impact into this. Okay, HDD will give an impact, and in normal also we see nowadays HDD laptops are also in boom, so we cannot compromise it. We can surely remove hybrid and flash storage because it's almost contributing nothing in comparison to all other features. Hybrid and flash storage are not contributing anything, so we will be simply removing them. So we are dropping it, and now we are left with only these columns. So we see that we have pre-processed CPU, we have pre-processed screen resolution, we have pre-processed memory. Now it's turn for GPU. So if you look for GPU, we see the same kind of thing. Like now over here in GPU, it's very simple. We will not do any kind of our HD graphics 620 anything. We will just get the name of the company, of which company does this GPU belong to. Is it of Intel or is it of AMD? Is it of Nvidia? That's it. We will not consider the model name or anything, we will just see the company name only. Okay, so the same thing, this is just an input dummy thing. This is what we will be doing. We will just extract the brands. So iloc is nothing but index locate. So locate the first index. So in the first index, what do we have? We have this Intel HD graphics 520, and then split it and then extract the first part of it, so we get the Intel. Okay, now over here we will do the same kind, this logic only we will be applying, this logic primarily we will be applying here for every column, and then we will assign the result of this into GPU brand column. So we are making a new column named as GPU brand, and then we'll do a count plot. The same kind of methodology we have followed like 5 to 6 times. So just understand the the power of this lambda function. Lambda functions are very important, and they are very time saving as well, because they are in place, they're just shortcuts for in place for loops. Okay, so over here we find that most of the GPU brands are Intel. Most of the other major contributing companies NVIDIA, and then we have AMD, and ARM is almost like negligible, so we can ignore ARM. So that is what I did. So df of GPU brand not equals to ARM. So I'm saying this df of GPU brand not equals to ARM will return the series, or will return the data, or will return the rows which are not having ARM, which is not having ARM as the GPU, and then we are just storing that data frame, and then we will do the count plot of this. So we will be getting the AMD, Intel and NVIDIA. Now we will, as usual, whenever we create new feature, you must have observed the pattern that whenever we are creating new feature, we are checking the relation, or the how it is inflating the price. So the same strategy we will apply here also. We will see how GPU is inflating the price. So over here we see that NVIDIA is almost like getting more popularity here, and NVIDIA is little bit costly as well. GetForce, GX, there are many kind of variations in NVIDIA GPU as well. So yeah, there is a little bit of variation in this as well. And over here we use median. We can also use mean. Let's see what happens when we use mean. You can even use median, you can use mean. There's not that much difference here. If you use median or mean or whatever, you get almost like same kind of results. Yeah, so GPU column is also pre-processed, and now we will simply drop the GPU column, because we are having the GPU brand here. So you must have observed a pattern that we are selecting a particular categorical variable, doing text processing in it, generating new features or generating new columns, and dropping off the previous feature or original column, because the new column is giving a lot of correlation, or is giving a lot of insight, or is contributing a lot towards the dependent variable, that is price. So that kind of methodology we are using here. We'll select a categorical column, we'll pre-process it, we'll generate new columns, and we will see the correlation of the new columns. We will see how the new columns are inflating or infecting or affecting the price or the dependent variable. If they are affecting more, we will drop off the original columns. If they are affecting less, we will drop off the new columns. Simple logic. Then we will do the same kind of analysis with operating systems. We will see that Windows 10, no operating system. Oh god, no, there is no operating system. There are laptops even there. So I think so the operating system has not been mentioned. No OS means operating system has not been mentioned. So Linux, Windows 7, Chrome OS, Mac OS, Mac OS X, Windows 10s and Android. Over here also we see that there are variations of Windows, like Windows 7 we will keep, Windows 10s, this can be included in Windows 10 only. Yeah, so we will do the same kind of analysis here. We will see the variation of price and operating system. We see that Mac OS, we know that Apple laptops are very costly, and Mac operating system is a very integral part of it, and we see that it is playing a very major role in the price inflation as well. The average price of Mac OS laptop is almost like 80,000, and the maximum can go for more than 1,25,000 as well. Windows 10 also we see most of the common people use Windows 10 or Windows 7. You may see Windows 7 also. Windows 7 is like there are few laptops which are getting more popularity also. In Windows 7 you can see that there are few laptops which are even touching 1 lakh. It's kind of craze. It may be only one within like 500, but it is. And Windows 10 is like most of the public use it, and that is why it's range into this. So this is like a scalable laptop. We will get out the unique things, and then over here the same strategy as we did it in case of Intel i3, i5, i7 and other. The same kind of strategy over here. We will club Windows 10, Windows 7, Windows 7s, Windows 10s into Windows, Mac OS and Mac OS X as Mac, and then other one will return other operating system. Instead of other, we can write other operating system to be more specific, or just write other as it is. I prefer to write as other only. So Windows 10, if the text is, so we are defining an category like set category function which takes in an argument as text. If the text is Windows 10 or Windows 7 or Windows 10s or Windows 7s, this is 10s not 7s, so just return Windows. If it is Mac OS X Mac OS, just return Macs, otherwise you return other. So df of operating system is equals to df of operating system dot apply lambda x set category of x, and then df dot head. So we will we have set the operating system thing as well. OPSys, this thing has been updated here, as you can see. Operating system has been updated here. Mac, other Mac, right? Apple laptops is Mac. There is one HP laptop which is not using Windows. That is the one. Okay. Then we will do sampling, and we see that Windows laptops are most common. So we did that, and we will see the count plot of it. We see that Windows obviously will dominate, Mac also, and we find that other operating system laptops are also there. So yeah, we will see the price variation. Mac, though we know that always Mac was kind of dominating, and over here we see Windows as well. Now weight analysis. Weight is a continuous variable here, so we will be plotting disk plots. So if we plot a disk plot, we see a kind of like a kind of Gaussian distribution. If it just kind of make some changes into it, we can make into Gaussian. Variation of weight with respect to price, we see that it's almost like scattered over here. Like the weight of the laptop, if it's in between 1.5 and 2, the major portion of the laptop lies between this range, like 60,000 and 0 so like 60,000. So we see that most of the common people use that kind of mentality, like the laptop weight should weigh from 1.3 to 1.3 to maximum 2 kilograms of laptop, and the price of the laptop is almost like 50,000 or so. And that makes sense. That is completely true from the scatter plot as well. A few laptops like 4.5 kilograms and they are weighing almost like this. They're not considered to be as outliers. They are considered to be as kind of giving good insights. Now we'll do the price analysis. We previously saw that the price was left skewed, kind of left skewed. Now this is very important here. Very important step. This is kind of left skewed, right? If we try to do a log on the values of this, what happens? Let's see. If we just try to do a np.log here, we see that it just gets converted to centrally distributed. This is now perfect Gaussian. This was left skewed Gaussian, but now this became centrally Gaussian, and this is very important now. So we will be updating the price of this into logarithm, like we will be applying the np.log here in future. Let's just see, because whenever there are features which are following Gaussian distribution, there is more likely that you will get very good results. and then when you do the correlation analysis, we find that almost we made very good features out of raw text. And then over here we see the correlation now. Previously, if you observe the correlation, we had very bad correlation things. We had like let me just show it up. Yeah, we used to get this big yellow chunk here, and now we just observe here how we reduce that multicollinearity thing into this very beautiful correlation heat map. So this correlation, with this last correlation, we end our exploratory data analysis part. I know this is this was a little bit lengthy because this involved a lot of pre-processing and a lot of visualization, but trust me, if you are good at doing all this, you are getting a good skill under data science and under business analytics as well. So one has to be very proficient in EDA. Okay, so do practice this, and I hope you understand whatever has been conveyed, and we'll look up to model building in the next video. Thank you. Alright, so in the last video we saw, or we completed the exploratory data analysis part, which was very long, and now we will move ahead towards model building. Yeah, so as I in the last video, as I said that the price variable or the price column had a little bit of skewness in its distribution. It was left Gaussian skewed distribution, or left skewed Gaussian distribution. We wanted to convert this left skewed to centrally skewed distribution, so we applied, or we tried to see whether log transformation can work or not, and we saw that log transformation actually changed the distribution from left skewed to centrally skewed distribution. So what we will be doing is, there is a simple kind of trade-off between logarithm and exponential. So what we will be doing is, we will be converting the price column into log of price. So that means let's say that our price is let's say, for example, df of, if we just type in df of price, let's make it as a list so that it becomes easy for us to understand the code, right? List of this, yeah. So we see that we get this kind of price. Okay, now if I do np.log of this price, what would I get? Just see, np.log of this value basically. Okay, copy, paste, and let's see what we get. Yep, we get almost like 11.175. that is almost like 11.175, 11.17. it also you can consider, because this is trailing here. So what the idea is, now if I do np.exp of this value, okay, np.exp of what? Of this value, right? Let's see whether we are getting 71,000 or not back. Yeah, we are getting the same result. So did you observe one pattern? Normally the distribution was left skewed, and left skewed is not that preferable. We want centrally skewed data. So for skewing it centrally, we applied a logarithmic transformation, and we saw a little bit of change here. We saw that this transformation, data from here, it got transformed to here, and this is very good. Actually, we want this kind of thing only, because we would get good results. So what we did is, we took an example. I took some 5 samples, and then I took this logarithm of this example. For example, I took logarithm of this value. I got 11.175. Now this 11.175 is lying here. You can see 11.75 would be somewhere around here. So 11.75 is sampled from a Gaussian distribution, or we can say uniformly Gaussian distribution. It is perfect bell curve. Over here, if I try to see where 11.75 is, it is somewhere around here, 11.75. And we can see if I want to sample also, I cannot sample. Or maybe in another analogy, you can think that 71,378 is somewhere around this, is somewhere around here. But this may get me into issues. So I want, on safer side, I want a centrally skewed distribution. So I converted this into log, and I picked up 11.175 from the central domain, so that the probability of me getting prediction is higher. Okay. So the whole aim is, whenever you check the distribution of any feature, always try to see whether the feature is following Gaussian distribution or not. Gaussian distribution or Bernoulli distribution or any other kind of statistical distribution or not. If a particular column is following XYZ distribution in a skewed manner, then try to apply some transformations like exponential transformation, logarithmic transformation, Box-Cox transformation. All this kind of various kind of transformations, if you Google, you will get some kind of code over there. Just simply copy and paste the code and then do the transformation and then check the result as we saw over here. Right. So if we try to convert our convert our features into Gaussian distribution, it will always be helpful, because Gaussian distribution has almost like constant mean and constant standard deviation. Z is equals to x minus mu by sigma. Sigma is standard deviation and mu is mean. It has that Z score value, and whenever you are sampling from a Gaussian distribution, there are high chances that you will always get good result. There is a lot of math behind Gaussian distribution, but they just on a nutshell, just remember that if your all features are following Gaussian distribution, your features are very good, your features are perfectly pre-processed, and they are ready for model building now. Okay, so for a slight change, I just converted them into logs, right? Okay, so that is the reason why I said, and we know that price is our dependent variable, so that is our test set, and the training will be df.drop price, right? So let me execute this. So now I have train and test separated. Now these are few imports which we have to import. sklearn.model import, train test split, then min max scalar, standard scalar, pipeline, column transformer, label encoder, one-hot encoder, metrics, randomized search, CV, linear regression, lasso regression, ridge regression, decision tree regressor, random forest, gradient boosting, XGB, SGR, SVR, K nearest neighbor, and sklearn import tree. We will be using ensemble method here. You will see how ensemble methods always give good results, but we'll see how here they are giving good results. So let's execute them. And train test split, the test size is given to be 0.15% of the total, and random state is 2. And then we see that almost 1100 rows are training and 196 are used for validation. Now there is a class which is named as which we imported, named as column transformer. We widely use while building our models using pipelines. So for this, we have to give index numbers as our columns which are having categorical variables. So for categorical variables, we will try to separate. Column transformers are basically used for categorical variables. So we need the use of the categorical variables here. So in order to kind of iterate easily, I am using a hash map over here with an index. Like for 0 we have company, for 1 we have type name, and so on. So if I shift enter this, so I get it. And now we'll use linear regression model. Let's see what linear regression model is. We will apply one-hot encoding on the columns with the indices 0, 1, 3, and 0 is nothing but company. This is a categorical variable. Company like HP, Microsoft, Google, Dell, etc. And 1 is nothing but type name, notebook, pro, game station. All these were type name as we saw. And operating system, Windows operating system, Mac operating system, other, and Linux. And 8 is nothing but CPU name. Okay, and 11 is nothing but GPU brand, Nvidia, AMD, Intel. All these are GPU brands. So for them we will be applying one-hot encoder. The remaining we will pass through it as no column is getting affected except the ones which are going into transformation. So step 1 is equals to column transformers is equals to column TNF, one hot encoder, sparse is equals to false, drop is equals to first, and then the column name. So basically what it is saying is, in column transformer, this will basically select from column to column, and sparse is equals to false. In the sense, what do we mean by sparse is something like this. See, I'll show you what sparse means. Sparse is when you're having a lot of zeros in your matrices. Okay, so if I'm having this kind of situation, 1 0 0 0 0 0, this is very small. But what if the count of zeros go till 1000 or so? So that becomes a sparse matrix. You can a better way or a simple example is an identity matrix of dimension 1000 cross 1000. So what happens in an identity what happens there? The diagonals are 1, rest all is 0. So that is the best example of sparse matrix. Okay, that is the best example of sparse matrix. And sparse matrix we kindly use as a data structure when we are having graphs which are not that much connected with all other components, and we have to apply some graph algorithms like BFS and DFS on it. So instead of using adjacency matrices and adjacency list, we use sparse matrix over there, because there are no many connections, there are less connections. So we will ignore all the connections over whichever there is wherever there is a 0, we will ignore it and only will consider the one part. So that's almost like a diagonal part. So that is the meaning of sparse. So we do not want any kind of sparsity in our data, in our transformation. And drop is equals to first. Now this drop is equals to first means what? Let's say that you are having okay, let's say that we are having some 3 brands like Windows, and then we are having HP, and then we are having Windows, we are having Mac, and we are having Linux. Okay, so these are the 3 categorical values which the operating system column has. Great. Now let me assign a value for Windows. Whenever there is window, that means it is 1, and this is 0, and this is by automatic 0, right? Whenever there is window, it will be 1, otherwise it will be 0. Whenever there is Mac, this will be 0, this will be 1, and this will be 0. Is it or not? Now just see, whenever there is Linux, this is 0, this is 0, and this is 1. So you observe one thing here. I do not require this Linux column at all. Why? Because if your laptop is Windows, then I don't require Mac or Linux, right? So I can reduce on Linux. When I'm having Mac, I do not require Windows and Linux, so I can reduce on Linux. Okay, when I'm not having either Windows or Mac, that means the operating system is nothing but Linux only, because there are three type of operating systems, and in your selection 2 of them are false. That means the third one is automatically true. So that is the meaning of drop. So this column transformer internally has this logic of dropping few columns but preserving the importance of that column. So that is why this is drop is equals to first. Okay, and then 0 1 3 8 11, drop is equals to first means you can either eliminate Windows also. So this means whenever Windows is 0, that means whenever Windows is 1, that means Mac and Linux will surely be 0. That means only then Windows will be on, right? So the logic is same. The main aim of drop is equals to first is drop a particular column but preserve its importance. That is the main aim. Okay, so as we all saw that these are all the categorical variables 0 1 3 11 0 1 3 8 11. So we'll be sending the index list of it, and then remainder is equals to pass through. That means simply pass through and make some changes. So this is step 1. That means converting. In short, if I say step 1 is nothing but converting the categorical variables into numeric variables. Step 2 is nothing but linear regression. Okay, linear regression model. Step 2 is like an object of this linear regression, and step 1 is nothing but object of this column transformer. Now what is the pipeline? Pipeline is nothing but list of objects. Now what are the objects over here? Step 1 is the object and step 2 is the object. How does a pipeline work? First it will see what is the first step, it will execute it. If there is an error, it will throw an error. If there is no error, it will go to the next step, right? So the same. So in pipeline, it is nothing but what? Set of tuples, or we can say that a list of tuples. We can say list of tuples only. No, this is right. So this is a tuple. So in order to identify a particular object, we need to mention some kind of label to it. So the label is step 1. So what is step 1? Step 1 is nothing but conversion of categorical features to numerical features. So in a pipeline, whenever you are running your, whenever the code is getting run, it will first check. Oh, so first we have to convert the categorical variables to numerical variables. So the label of that step is step 1. Then the next label is step 2. That means we have to, now we converted our categorical variables to numerical variables. Now we have to apply an algorithm, which is nothing but linear regression to that converted numerical variables or the entire data set. So that thing is labeled with what? Step 2. So this entire thing will return what? This entire thing will return a pipeline, and we store it in a pipe object. Then we fit it. Fit in the sense what? We will pass the data to this pipeline. That is the meaning of fit. And then we will predict. Once we do this, what we get? We get a metrics.r2 score. Now what does R2 score is? In classification, how we are having accuracy, in the same way in regression problem statement, we do not use accuracy. We use R2 score. R2 score gives the idea of variance of how one particular feature or how a set of features are inflating or affecting the overall dependent variable, which in this case is price. So the R2 score 80.7 means 80.7% of your features are giving good result. Or we can say that the features whichever you are using, they are giving a result of 80.7%, or they are giving a result of they are giving prediction up to an accuracy of 80.7%. We can say in that way, in simple words. Okay, so in classification we have accuracy score, but in regression we will be having R2 score. We will see the error also, mean absolute error, MAE. So mean absolute error is what? Mean absolute error is 0.21%. Okay, or we can say 21% or 0.21. Now MAE is 0.21. If you want to check how much there is a difference to this, we see that if is there any difference as per the original value or not? Yeah, this is nothing. So yeah. So this is important now. The MAE value is what? 0.21. Okay. Now if you do np.exp in 0.21, what do you get? You get 1.23367. Okay. Now what does this 1.23367 mean? This means that the value over here was what? 71,378 point something. This was the thing, right? So if I try and subtract, if I subtract this with np.exp of mean absolute error, that is 0.21011782, let's take it so how much am I getting? Yeah, you see the variation over here. Okay, 78, this is our original price, and this is the price which is predicted by our machine learning algorithm, which is linear regression. What is the difference? The difference is nothing but 1.23. That's it. That is a difference. So if I include this entire MAE, what will be the difference? There will be no significant difference in this. You can see over here, almost same, right? Almost same over here. So 449. That means from 49 to 68, if you go, it's like 59 and 18. That's it. 18 units, you can say. That means linear regression is giving us an error of almost like 0.2%, not more than that, or 2% we can say. But this is only for first one. We cannot conclude it for everything. Okay, because the R2 score is almost like 81% here. Let's try out other models. Now we'll see ridge regression model. So the same concept, we will be applying the column transformer, that is nothing but one-hot encoding. The same procedure which I said in step 1 is followed. Then in step 2, instead of using linear regression algorithm, we'll be using ridge regression. Now speciality of ridge regression is it is having some hyperparameters and it is having some tunable parameters which we can tune using hyperparameter tuning and can get good results. So the same thing, pipe is equals to pipeline of step 1 and step 2, and then we'll see pipe is equals to pipe dot fit and this. Okay, so if we predict, we get this kind of result. Over here MAE was 0.21, over here MAE became 0.20. There's no significant difference that much. Let's try lasso regression now. So in lasso regression, if we try lasso regression, only thing we have to change is this step 2. Rest everything is same. Just what we have to do over here, just we have to do Control A, Control C, come here, Control V, and then over here instead of ridge regression, just type in lasso regression and whatever parameters or you want to give, you can give. That's it. If you execute this, what we get? We get almost like 0.80, 0.2114530 as MAE. So ridge regression, so lasso regression, it gave me 80% accuracy. Ridge regression gave me 81.2% accuracy. This gave me 80% accuracy. So in linear models, we can say that ridge regression is performing good. Now in the next video, we will look out for ensemble models like tree based models. We'll look out decision tree, random forest regressors and many more, and we'll come to a conclusion that tree based models are performing very good. See you in the next video. So in the last video we saw linear models and we came to a conclusion that ridge regression was giving good result without hyperparameter tuning. We saw that the ridge regression was giving almost like 81% accuracy, or it's like 81% it is giving good result. Okay, now we will see how decision tree or tree based models work. So over here we will apply the same concept of pipelines. So step 1 would be same, so as it is I copied step 1. Then step 2, we will initialize the decision tree regressor class. Here the parameter we are giving as max depth is equals to 8. Now this parameter is a hyperparameter which needs to be tuned. It will be tuned if we get a very good result now. Okay, so I will explain what this max depth is. So in decision tree, what is the main funda of decision trees? Let me just explain. What it does is, if the dataset is something like this, for example, the dataset is something like this. Okay, the dataset is something like this, and here we are having some two classes. Okay, what are the two classes? We are having two classes as maybe this is a classification thing, but still it will work. Okay, the two classes are star and circle. Okay, so the first split would be something like this. The decision boundary of this decision tree algorithm would be something like this. It will split first here, then what it will do is it will split here, then it will split here. Okay, then it will split here, then it will split here, then it will finally split here. So you see one thing here, how many splits happened here. This entire portion is one particular unit, this is one particular unit, this is one particular unit, 4 particular unit, 5, 6, 7. So this is 7. So for this small data, 7 splits were done. Now you see in 7 splits, in each split it categorized data very, very accurately. See, if you observe this part over here, if you observe this part, if you observe this part over here, if you observe this part over here, these all classes are one part. They have been classified correctly. This star, there is only one class of the star, but it is also classified correctly, right? This group is also classified correctly. This only single thing is also classified correctly. Only there is a misclassification over here, and over here also it is correctly classified. So there are almost like 1 misclassifications out of 8. Okay, so out of 8, totally there are 8 misclassifications. So what will be the percentage? It's almost like 95% above accuracy. But you know what? This condition is known as overfitting. So this decision tree or ensemble methods, whatever we try to code, we have to be very careful when we are learning because these kind of algorithms, they run at the very end. They classify till the very end. Okay, so what do I mean by that very end is basically until and unless you get a pure sample. Okay, let's say that I am having some two classes. Okay, let's say A class and B class. Now A class I am having 40 samples and B class I am having some 50 samples. So in total I am having 90 samples, right? So I will start my decision tree from this node. So from this node there is some condition or decision which is made. Over here also there is some condition and decision which is made. Okay, so over here A sample class I got something like 40, I got something like 30, and B class I got something like let's say that I got 30 over here. So out of 50 I got 30 here, and out of 40 I got 30 here. So this is still impure. Okay, this is still impure because there is having this node is having pure impurity of both A class and B class. What my requirement is, I should only get either A class or B class. Until and unless I get either A class or B class, I have to go splitting. For positive class, if I say that A class over here, let's say that A class got 25 correct samples and B class got, let's say, 30 correct samples over here. Still there is impurity here. So based on some decision, again I will split this. Here also based on some decision, again I will split it. So if it is 30-30, let's say that over here A got 15 and B got, let's say, 40, B got something like, let's say, 15 again. Okay, still there is impurity here. The classification is not getting done correctly. If you want to if you are into metrics and all, so this is 60, right? So let's say that out of 60, let's say that 15 were A and 45 were classified as B according to the decision logic which was made here. There is still impurity. Over here there are total of 55. So over here I will again say that this was 25 or this was 20 and this was like 35 based on the some decision logic which was made. Okay, again there is some split. Until and unless I get either 15-0 or 45-0, I will split. I will go on splitting. That is the main aim of this decision tree if it is not properly setted. Okay, so if I just leave it, so this will take a max depth of how much, you know, by estimate it will take a max depth of almost like 25, and max depth of 25 means in the previous thing which I showed you, this complicated decision boundary over here which was having many kinds of ups and downs, this which led to overfitting is nothing but because of this max depth parameter. So the max depth parameter is very important in decision tree and it should be tuned correctly, and for that we use hyperparameter tuning, which we will discuss later. I hope this makes sense. So now over here max depth we kept it as 8. Okay, and then the same story we will apply the pipeline over here, which is column transformers, and then step 2 is nothing but our decision tree digressor object, and then we will fit it, and then we will predict it, and then we will see what is the R2 score and metrics.mean. So we see that the R2 score was 84.66. that means accuracy in terms of regression is 84.6, right? Let's move ahead. That was decision tree. Now coming to random forest has its own guys. Random forest is very awesome algorithm, and obviously this gave us very good result, as we can see 88.4. So random forest has many parameters over here. Random forest is nothing but a bagging technique that uses bootstrapping and aggregating. So what does this bootstrapping and aggregating mean? Okay, let me just show you what this bootstrapping and aggregating mean, right? So what happens is you are having a data set over here. Let's say that the data set size is some this is having some 1100 rows, for example, and this is the column. This is the column which we want to predict, right? So what happens is for the first 50 columns randomly I will select. Okay, so this is nothing but bootstrapping. Bootstrapping means randomly select some samples from it, run a decision tree classifier onto it. and get the score of the decision tree classifier. Let's say that yes count is almost like yes count is 20 and no count is let's say that S count is 80% and no count is 20%. Okay, so this is decision tree 1. So bootstrapping means subsampling from the original data set, okay, where the sampled data set size is less than the original data set size. That you should keep in mind. And aggregating means what we are aggregating? We are aggregating this algorithm. That is nothing but aggregating is nothing but pushing the algorithm into that subsample, or running the algorithm into this subsample which is extracted. So decision tree, it was run on this 50 rows and we got the result as 80% was yes and 20% was no. Great. Now what we will do? We will subsample again. Let's say that from this was top 50. So I will select now from 30 row, 30th number row till 80th number row. So this on this subsample I will run decision tree 2. Decision tree 2 I will run, and this decision tree gave me an result of yes was something like 85% and no was something like 15%. Okay, and no was something like 15%. Okay, then what I will do? The same process I will repeat. Now I did it from 30th row to this. No, now we'll do from 50th row to 100th row. So from 50th row to 100th row I will run D3 decision tree 3, that is third instance of decision tree. And over here I observe that yes was something like 80% and no was something like 20%. So like this I will be running so many decision trees and I will be doing so many kind of samplings and everything. So by this what is happening is the algorithm is learning from sample by sample by sample, and it is extracting information from sample by sample by sample, and it is collaborating them. So at the end what will happen, D1, D2, D3, so on till Dn, how many ever decision trees we are using, this all the results. If it's a classification problem, then we will see the majority. What is the majority count, whether it is yes or no. Like every decision tree is giving 80% yes, 80%, 85% yes, 80% yes and all. So we will see how many such trees gave us that kind of result, and we will finalize that. Okay, and if it is no side, we will also see on the no side simultaneously. That is in case of classification. But in case of regression, what will happen? In case of regression, we will do mean. Okay, over here let's say that let's say that actual price was something XYZ and predicted price by this decision tree sample, by this decision tree on this sample was something like DEF. So we will find the mean absolute error of that, and we will pick up the decision tree which is giving us the least mean mean absolute error, and we will finalize that. So this is the whole idea of this is the whole idea of bagging technique. That is nothing but bootstrapping plus aggregating. So this is the entire working of how a random forest algorithm works. I didn't go into very much detail. I just gave you the overview, and the math behind this is little bit complicated because it uses some kind of impurity scores like Gini and impurity to calculate, and there are various other parameters of decision trees also which we need to tune. So the number of decision trees, these are determined with the help of this parameter known as n estimators. So over here I kept as n estimators to be 100. That means I'm using some 100 decision trees, and random state is equals to 3. That means whenever I'm running this algorithm, the state should be 3, or wherever the data set is been selected, that should be in the state 3. And then max samples I'm taking out to be 0.5, max features to be 0.75, and max depth to be 15. Max samples and max features, they are going analogous to each other. That means in a decision tree over here, max samples and max features means over here, in order to save the branching cost, we will be selecting some kind of limited features only. That is the meaning of max sampling. Okay, so this is my random forest classifier, random forest regressor, which I declared this class, and this class object is nothing but step 2, and then the same pipeline, and then pipeline.fit, and then pipeline.predict, and then metrics and R2 score. Let's see what we get. We get 88.4% here. So this is a very good algorithm, and I will be using this algorithm for prediction now. Okay, so yeah, we will be using this algorithm now, and we will be storing the results of the algorithm now. Okay, so yeah, so I will be storing this. So this is nothing but import pickle.dump and all these kind of things have been done. Just execute it, and the model will be saved here, and then train.head and then trainhead.csv and everything. So now that was all about for the model building of decision trees and random forest, and we saw that random forest algorithm gave us a very good result here. Okay, and we will look forward for hyperparameter tuning in the next video. Till then, do practice this. Hi. So in the last video we saw how these parameters were very important, and these parameters were our hyperparameters, as I said. So we need to tune them. So we will be using a technique known as hyperparameter tuning, and we will be using a randomized search CV, which will give us the best hyperparameters for our random forest model. Why we are particularly selecting random forest model? Because random forest model gave us a very good accuracy over here. That was R2 score over here, that was 88%. So we'll be going forward with that only. So you can also hyperparameterize the other linear algorithms as well, linear models as well. But time being, I'm using randomized. I'm using random forest algorithm. So let's see what we get. So over here, I need to get the transformer list. That is nothing but the categorical list, and then I will apply the get dummies function from pandas, and I get this train. And then over here what I will do is I will apply train test split. Okay, once I apply train test split, so basically I am going in other direction for only the random forest classifier, where instead of using column transformer for kind of getting this thing, getting the categorical variables, instead of using column transformer, I am using get dummies. Get dummies is also one-hot encoding only, and the same kind of result we will be finding if we use column transformer also. There's no difference. Then I will use train test split, and then yes, this is a very important one. Regression object is equals to decision tree regressor random state 0. I'm fitting it, and then I'm plotting the decision tree. Now you just understand, in the previous past video I said that when we are building decision tree, it will try to go till the end. Now you will see that how it is trying to go till the end. Okay, so this will take a little bit time, and you see how much tedious calculation this is doing at each node, right? This will do a lot of calculation because this is not perfectly hyperparameterized. The max depth is not set, the criterion is not set, anything is not set over here. It is by default taking some random value and it is doing it. And you see how bad and how big the decision tree would look, and we see that the execution time is also taking too much. Okay, so this kind of model, when it goes to production, this kind of model becomes little bit heavy, and this kind of situation takes a lot of computational power as well. So yeah, we have to be very careful here, and we will see something over here like let the decision tree get plotted. I think it is taking more time than required. Yup, we get the decision tree here. So if we see the decision tree here, oh my god, this is so much. So I have to scroll a lot down here. So if we see this very big, you can see this last end, it tries to classify this till this last end, and to be honest, this much big decision tree is not required only. Okay, we can cut or we can prune this decision tree. Prune in the sense cutting, not require everything, but require only the important part from which we can manage the things. That is what we are looking in decision trees. So you see that this is totally in case of overfitting only. But when this kind of decision tree object is made into production, it will give you blunder results. So we have to optimize this. So for optimizing that only we are using this hyperparameter tuning technique. So how we will go ahead with this? Okay, so this is how the basic tree looks. So there is some parameter known as cost complexity pruning path. This cost complexity pruning path is responsible for pruning the leaves or pruning the branches of this decision tree. Now on what factors does the pruning happen? The pruning happens on the factors like there are various factors which affect pruning. There's no such exact factor which takes place, but I will just give you a glimpse of what actually this is. It says that cut off or chop off the branches. When you are having something like 50-50 kind of situation or like 75-25 kind of situation, you keep that. You allow a little bit of misclassification, because in future you will be getting data. You will be getting a new kind of data, and if your model is already overfitted, the model will always try to predict whatever the model has been trained on. Let's say the model has been given 100% accuracy for a label yes and 0% accuracy for label no. If you give a new data set, if you give some new data point, it will by default classify it as yes. It will not even check whether it can come under no or not, even though it was no. Human brain can say it as no, but your algorithm is saying it as yes. That means that it has totally overfitted. And when it comes to totally overfitting, this is the scene which happens. This big decision trees. So we have to chop them off. So in order to maintain consistency, or in order to maintain some kind of computational stability with precise accuracy, we use complexity path. So this is nothing but cost complexity pruning path, and when we execute this, we get the CCP alpha values, and CCP alpha is our main hyperparameter, along with max depth, n estimators, min samples leaf, min samples call leaf. So by these 5 or 6 parameters, random forest algorithm must be hyper tuned. So when you try to look at CCP alphas, what you will get CCP alpha is, you will be getting something like this. If you try and see, you will be getting a numpy array of values. So we will be using this over here. So for alpha in CCP alphas, regression is equals to decision tree regressor of alpha, regressor.fit xtrain ytrain, and alpha list dot append regressor. So we are appending this regressor models into this. When we do shift enter, this will take a little bit time because it has to process this all CCP alpha values, right? Yeah, it has to process those all CCP alpha values. And once if we see the alpha CCP alpha list, once if we see the alpha list, you will understand. See, decision tree regressor alpha CCP alpha is equals to 1.67 random state 0, 1.670 random state 0, 1.25 random state 0. So this alpha list is having objects of decision tree regressor. Now we are already having decision tree regressor, no? So we will apply a for loop and we will calculate the training score and testing score. So reg.score xtrain ytrain, reg.score xtest ytest. Or maybe this should be something like yeah, basically the regressor object has only this thing only, reg.score xtrain ytrain, reg.score xtest ytest, and CCP alpha is the x label and accuracy is the y label. And then we are plotting using matplotlib, and then if we shift enter this, we will get the plot. Now the plot is shown here. Yeah, so how do we select the best CCP alpha from this will be our new question. So over here if we try to look, this thing, okay, this is right. So over here if we try to look, alright, so over here we find that this red line is nothing but testing, and magenta line is nothing but training. So what is happening is, training is coming like this steeply down, and testing is coming something like fluctuating like this in between. Too much of fluctuation over here, and then steeping down, and then steeping down, and then ending here. So this is the kind of situation which is happening over here. So we have to find the CCP alpha in this fluctuation only. Fluctuation in the sense, after what sudden cause or what sudden parameter the testing score just rapidly decreased down. So we observe that over here the crowd is over here, the main crowd is over here. So this entire thing is lying in between what? It's almost lying in between 0.00 to 0.0025, right? So we'll be applying our CCP alpha values in list in between these values, that is 0.000 to 0.0025. So we'll be applying that kind of logic here. So here that is what I have written. Possible values can lie from 0.0025. Note that this is 0.025. I'm saying 0.0025, which is somewhere around this path, okay, to 0.0075. Now 0.0075 is still less than 0.025, right? So yeah, this will lie in between this. So if, for example, if I keep my CCP alpha value to be 0.0085 and if I try to run this, you see this, how short and simple this decision tree is, or decision tree regressor object is, okay, how short and simple the decision tree was made. And you can see MSC also, at each node MSC was constantly decreasing. It went till 0.13, here it went 0.084, and it classified correctly 106 samples. So MSC is falling down, you can see. Instead of going too deep, you are going to till an optimal deep. That is the main name of cost complexity pruning path. Now we will try to do some hyperparameter tuning now. So decision tree model is here and random forest model is here. So if you notice that this is a kind of JSON, which is this is a kind of JSON which we are using, and JSON is nothing but nested dictionaries inside it, okay. So random forest model, random forest regressor, and an n estimator is this, criterion is this, max depth is this. How on earth can we know this? These parameters are existing? Just click over here and then just shift and tab. Once you shift tab, just expand the widget and then scroll little bit up, scroll this up, and over here you can see this max depth, min sample split, min samples leaf, min fraction weight, max features, min impurity decrease, bootstrap, n jobs, random state, verbose, CCP alpha, max samples. Everything is given here. So based on those criterions, I'm using that, and then I'm executing this. And this is, as this is a randomized search CV, this would be a little bit fast. So for model name and MP in params.items, what will be the param.item here? Params.items will be random forest, decision tree. These are all the no. What are params.items? Params.items are this thing is nothing but params.item. This thing is nothing but params.item. Okay. So params.item is nothing but key with the value. Okay. So for model name, MP in param.items, randomized search CV is equals to MP of model. MP of model is what? Random forest regressor. And param distributions is equals to MP of params. MP of params is this. CV is equals to 5, cross validation. N iter, that is number of iterations, and scoring. And you will be applying this algorithm on the randomized search by using the metric known as negative mean squared error. Basically in regression we use negative mean squared error, in classification we use accuracy. Okay, we can use any other metric as well, but most commonly used are these only. So I'll be going with this. And verbose is equals to 2 means it will show us what all kind of this is doing. At the end of each cross validation, we will know the criterion, max depth, max features, min samples, and also the total time which it took for computing the cross validation. And then clf.fit xtrain, and then scores.append, model name, best score, clf.best score. So this CLF, that is nothing but randomized search CV object. It has few parameters named as best score, best estimator, and best params as well. Okay, so I'll be storing this into a list. So this list will basically contain a dictionary, and this dictionary I will convert into data frame so that it is easy for me to know which algorithm I have to select. So I'll execute this. I'll press shift enter, and this will take a little bit time. As we can see, total time elapsed is 0.2 seconds, 0.2 seconds. Now here it is gradually taking more time, because gradually these estimators will also increase, and the CCP alpha values will also increase, and max depth will also increase. Again, I will say here np.linspace. I forgot to say np.linspace. Linspace is nothing but linear space, where starting is 100 and ending is 1200, and 10 is nothing but skip. Okay, so from 100 to 1200, you take any 10 values. You take any randomly chosen 10 values. That is the meaning of np.linspace. Linspace means linear space. So from that particular linear space, you will start from 100 and you will end at 1200. In this particular 100 to 1200 range, randomly pick any 10 values. That is the meaning of it. Okay, so other things are self-explanatory, and then over here it is taking a little bit time. As I said, that as number of estimators increase and max depth increases and CCP alpha increases, these things, they increase a little bit more. Okay, so let's just wait for the results, and we'll catch up in the next video. Alright, so in the last video we stopped at the we said that we would be executing this, and we would be wait until this execution gets completed, and we saw that it executed a whole heap long, and it took in almost like 2 minutes or 4 minutes for me to get executed entirely. So after this, what we will be doing is, as I said, that this course list is nothing but a dictionary inside. So we are storing a dictionary inside a list. So we will be unzipping that dictionary into a pandas data frame, and we'll see what are the results. And we see over here that random forest is giving like 0.0 best score has to be this. Neg mean squared error means you can ignore this minus, and you can see that 0.075 is the error which it got. So that means that is a very low error. That indicates, when the error is low, that indicates the accuracy or the prediction rate is high. So I think so this is giving a good insight over here. So if we just try to see, we'll be using this random forest classifier object. Random forest classifier object, we will be using this, and we will be placing it over here, and we will see what kind of results we are getting. Okay, so let me just, for safer side, what I will do is, we will just copy this and we will just paste it over here, so that, you know, if in case we are not getting good results, we can use this, because this already this configuration which randomly I chose already gave me 88% result. So if that is giving me 88% result, and this is giving me like 70% or more or less result, I will reject it, right? So I will just paste it over here, and this one is nothing but the one which I copied from here. So for safer side, I'll copy it again, copy, and then I'll paste, and then I'll just press shift enter, and this will take a little bit time. Yep, so we see that there is no change. Basically, it is also giving 88.4% result only. So this is giving a little bit better result, 88.4024, than the other one. Okay, the other one, I think so, gave us something nearly to be 88.24 something. So the same kind of configuration has been detected by our hyperparameter tuning also. So we will be using this random forest model, and we will be trying to predict on the entire data set. Now what do I mean by this entire data set? Let's, if we just see train, if I just hit train over here, we get this, right? So now in this train, what I need is, I need this train to be in a numpy array, because this RF object, if I try to predict, this is taking a numpy array, because xtest is a numpy array. So I will be converting this train into a numpy array. So test train is equals to np.array train, and then for I in range, len of test train. If you just try to observe xtest dataset, how xtest numpy array looks like. Xtest is basically this thing only. It's a pandas data frame. If you unzip it, it becomes a numpy array, and it will look something like this. Okay, it will look something like this over here. Just a minute, I'll just show it will look something like this. This is the outer list, this is the inner list, and inside the inner list you will be having values. So for what, so in test train is already a numpy array. So in that numpy array I am adding one more. So I am adding this list in order to kind of make things work possible. So I'll say rf.predict the numpy array I am passing, and then I will hit on shift enter, and this will be basically predicting on all these 1302 rows. So this will take a little bit time because it is running the entire code on all these 1302 rows. So basically what I did is, all these 38 columns are there now, 1302 into 38. I converted this entire data frame into a numpy array, and then this numpy array I passed as an I ran a for loop into it, that is this for I in range len of test train, and I passed each and every index, that is nothing but train of 0. If you do train.iloc of 0, train.iloc of 0, if you do, what you get, you will get the first index. Okay, you will get the first index value basically if you do train.iloc.0. Yes, this will take a time because over here this cell is already running, and I did some whenever this is executing, I shouldn't do this practice because this might affect the execution also. So I'll just cut this cell, that's not required, that's not important. Let this execution get done completely, and we are good to go now. We are good to go then. So this will take a little bit time, and then yeah, so this will take a little bit time because 1302 rows are already 1302 rows at once are being sent to it. So this will not take that much time, I think. Yeah, so we see that we get this numpy arrays. Now I will let me just revise a little bit when I talked previously about the transformation which I did, right? So you might be thinking that, hey, but the prices must be like 71,000 or so now, why it is like 10 or 20 or something like that? Yes, I'll answer that question in this way. So in some of the video, in the previous few videos, I said that the 75,000 thing is in the left skewed distribution, but 11 point something is equivalent of this left skewed distribution in the centrally skewed distribution, right? So the same kind of ideology will be applying over here. So if you just observe, if I do np.exp of this 11.175, I am getting 71,378, which is what I need, right? So I will be applying the same kind of logic here as well. So what I will be doing is, this is the numpy array. I'll say np.exp predicted of I of 0 for I in range len of predicted. This is array, right? So in array, this is the entire part. So how to extract this entire part? Array in predicted of I is basically, if I is equals to 0, that means this. Of 0 means this value only, 11.1380033. Okay, so for every index I am extracting the first value, as this is a 2D list, a list inside a list inside a list. That is the meaning of this. For I in range len of predicted, if I click on this, I'll get the answer. Okay, and then I'll store that answer over here. df of predicted price is equals to np.array of answer. So I get the np of array of answers over here. Now what I will do, now I will compare the answers. Okay, so sn.dispplot df of price hist is equals to false. I just need to see whether the distributions are matching or not. If I do this, I see this is not a very good result because I can see that this predicted price, it is not even reaching this 35k over here, right? It is just stopping by 3,50,000. It's not even reaching this tail end. It is just truncating down to 1,50,000, and by max it is going till 1.5. So 1.5 into 10 raised to power minus 5. So I don't think so this RF model, which is like CCP alpha equals to this, is a good choice. Instead of that, instead of using 1077 estimators, I'll be using this algorithm. Let us random forest CCP is equals to this thing, and I'll see what I'll get. So random forest version 2. So random forest regressor version 2, where estimators are only 100. So if I go with this 100 estimators, let's see what happens. I get an accuracy of 88.7. There I was getting an accuracy of 88.4. Here I am getting an accuracy of 88.7. So I think so random forest regressor version 2 is working good, and we'll see about the execution of this. Let's start the execution, and I'll pause my video over here because this will take a little bit time, as I said. So once this is executed, I'll continue in the next video then. So this took a little bit time, and finally I got all my predicted values. Now what I'm gonna do is I'm gonna do the same thing which I did previously. I'll say ANS is equals to np.predicted and all, and then df data is equals to df.copy. For safe side, I just took the copy, and then np.array is equals to this thing. And now if I try to look at the distribution plot, you see how smoothly it went. This is exactly what we wanted, because actual price and predicted price are going hand by hand over here, almost till like 45,000 or so. It is exactly predicting the correct result. After that only there is little bit of fluctuation which is happening, but that fluctuation is also not that much. Very rare fluctuation is there, and this kind of model, little bit of on outliers, this is not working that great. But there were only like 2 or 3 rows which were kind of outliers, and because of them only the accuracy was dropped till 88%. It makes sense in that way. So basically this thing is working very great, and I will definitely save this model using a pickle file. I will pickle up this model as laptop price predictor version 2.pkl, and I will write the entire random forest algorithm, that is RF model, in right binary mode. So I'll open the file which is known as laptop price prediction version 2.pickle, and then I will write the content of random forest regressor into that file. So, and then I will close the file. That is it. So finally we have made it through the entire code of laptop price predictor. We have saved all our model weights into this laptop price predictor version 2, and now we can head up towards coding the UI and unpickling the laptop price predictor version 2.pkl, and then working on the UI code. Thank you. Hi. So in the previous video we finished up with hyperparameter tuning, and then we saved up our machine learning model, which we said that we would be using a random forest model. So in that we saved 2 types of models. One was a normal pipeline model, and one was the random forest model, right? So we will be unpickling them, and we would be integrating those models with the UI here. So we will be using Streamlit for designing or for UI, and then we would integrate our pickle file with it. So let's start by importing the dependencies. So we will use Streamlit as st, pandas as pd, numpy, and pickle. These are the standard libraries which we will be using. And then I will unpickle the first, that is nothing but pipe.pkl. That is nothing but the model which gave us the accuracy or the R2 score of almost like 88.7%. So this, I renamed it as pipe.pkl. This laptop price predictor version 2 gave us an accuracy or R2 score of like 88.4%. So I saved, for better side, I saved these 2 models, but I will go with pipe.pkl because it performed little bit good in comparison to laptop price predictor version 2. Okay, so I will open this file and then pickle.load that file and then file.close. So whatever is the content in the file, that means whatever the weights or whatever the algorithm was saved in object notation is got stored into this object rf. Now over here we know that we have trained our data, so that means there were few changes which we made in the data, right? So that is why we also saved in our Jupyter notebook the trained data set, or the data set where we introduced new features, right? So we did a lot of exploratory data analysis, and in EDA we saw that how using existing features we can create new features which are giving much more insights as compared to the original features. So the new features which we used, we have separated them. So the company name, type name, RAM, operating system, weight, these all features were common in the original dataset as well as in the new dataset or the trained data which we generated. But the new features which were generated were touchscreen, IPS, pixels per inch, CPU name, HDD, SDD, GPU brand. So these were the these were the new features which we generated using the existing features, right? So we did a lot of pre-processing and we generated new features, right, in the EDA part. So all those features are these, and based on these features only we trained our machine learning algorithm, which is random forest. So we will be using that trained data.csv only. So we will use pandas for reading that, and then we want data of IP. This is just for simple purpose, data of IPS.unique, not an issue. Then we will set up the title of our website, which is nothing but laptop price predictor. We'll write st.title laptop price predictor. Then company is equals to st.select data of company.unique. So what this will do, select box is nothing but it is like this, and data of company.unique means it will select all the unique values which are there in it. That is it. Inside the select box we can see many companies, we can see the name of many companies. So that is all this select box does. And then the type of laptop is also a select box. So type data of type name.unique. So the same thing which we can see over here. Type name also we can see over here, ultrabook, notebook, netbook, gaming, 2-in-1 convertible workstation. And we saw also how type of the laptop is affecting the price and all, right? Then RAM present in the laptop. So we know that there are not more than one there is no more than 128 GB RAM. So just we normally instead of using data of ram.unique, I just gave this random list. You can also use data of ram.unique also, no problem in it, because the range lies from 2 to 64. But the thing is you have to convert its as type to be integer. That is not integer by default, but it is integer only. So no need, you can just pass in a list so that it becomes simple. Why to in fact use this data of type name.unique? This takes a little bit time as compared to this is just straightforward. Then we will use the operating system. Were only 2 or 3, so that is nothing but what Linux, I think when it comes to operating system, we are having Mac, other and Windows, right? So they are just 3 categories which we discussed. And weight of the laptop is st.number input, weight of the laptop like 1.37 kilograms or something we can the user can manually type in. Then we will see touchscreen, whether the laptop is supporting touchscreen or not. It's a boolean value, so it's either yes or either no. Same goes with IPS, it's either yes or either no. Then screen size, st.number input of screen size. So in screen size we do give the number input over here, like 100.45 or anything. So basically that screen size is nothing but pixels per inch only. So many of them it becomes little bit confusing when it comes to this thing. So after IPS we see pixels per inch. This pixels per inch is nothing but this thing only. Okay, no worries onto it. And then we have the resolution here. So basically what is happening, we will take in the screen size and we will take in the resolution. After we take in the screen size and resolution, we will apply the pixels per inch formula which we discussed above, now previously. We will apply that formula and then we will calculate it. So we will also provide resolution as well. You can see we have the screen resolution here. Then we will say CPU is equals to CPU name dot unique. Then hard disk drive also we will supply HDD as well, and GPU as well. The same thing, it's just we are just changing the list over here. It's the same select box which we are using again and again. That's it. In GPU also we will use the same. Right? And note that we converted everything in GB, right, at the end. Even if it was 1 TB is nothing but 1000 GB, so we converted everything in GB. So we made sure that our conversion rate is good. Now over here you see, if st.button predict price, if someone clicks on the predict price button, then what should happen? A PPA is equals to none. That's what I said, pixels per inch. We will define now pixels per inch over here, because our machine learning algorithm it just uses the screen size, it just uses this screen size and resolution into consideration, and then converts them into, and then uses them to create a new feature which is known as PPA. Now if touchscreen is yes, then we will say touchscreen is equals to 1, else touchscreen is equals to 0, and eventually we have to convert it into numbers. We said it as yes and no, but the computer doesn't understand category, right? So it has to get the number. So we have to typecast it over here. When the touchscreen is yes, we will say touchscreen is equals to 1, if else touchscreen is equals to 0. If IPS is yes, we will say IPS is equals to 1, else IPS is equals to 0. Then we know that in resolution we did this kind of mechanism. We figured it out, X resolution and Y resolution, and then we had this formula of PPA, pixels per inch formula, that is X resolution square plus Y resolution square whole square root by divided by screen size, right? So we will calculate this PPI function, PPI variable, and then query is equals to np.array, and we will pass all the variables which are nothing but company, type, RAM, weight, touchscreen, IPS, PPI. So in this train data.csv, if we see, after IPS we are having PPI, but normally in the dataset we were having screen, and we were having screen size and screen resolution. So we converted that screen size and screen resolution into a new feature, that is nothing but PPI, and we observed that PPI feature was giving almost like 50% of its correlation with price. So it was a very good feature which we created. Then we have CPU, HDD, GPU, and OS. Now this np of array, this is a double dimensional list. This is one list, and np.array will also make one list. So this becomes a double dimensional list. So we have to kind of reshape this. So query is equals to query.reshape 1,12, as we were having 12 features. So we are just reshaping this into 1,12. And then what we are doing, we all know that this random forest model is predicting the np.log value. Okay, so if it was 71,000 something, we had taken a logarithm so that the distribution of price becomes normally distributed. So the value of 71,000 something change when we did np.log was coming out to be something near 11 or so. So a random forest model will predict that 11, 12 values only. So we have to exponentiate that. So for that reason we are doing np.exp as well. Okay, rf.predict query of 0, we will get the price, and then we are doing np.exp on it. After we do all this, we will typecast it into integer, and in order to be little bit biased, we can add this kind of bias over here, like string of prediction minus 1000 rupees, or string of prediction plus 1000 rupees. This is not a bad idea. You can use it, because after all, machine learning is all about prediction, and it is no guarantee that exact prediction you will get every time, but there are chances that 80% or 75% of your model is predicting well and good. So that's not an issue completely. You can also add this kind of thing. It's not an issue at all. So after all this, everything is done, so we just need to execute it. So let's see with HP laptop, HP notebook. RAM I will select as 8 GB. Windows I will select. Weight of the laptop I'll say is 1.37 kilograms. You can be very specific by giving here in kg also. Okay, touch screen I will say no. IPS I'll say no. Screen size let me say it is like screen size. If I want, I will take this example here, and then I will see what is the screen size here. So screen size in inches is 13.3. So we'll take this 13.3 here. So 13.3 we'll consider. For example, resolution I'll keep it the same. This I will say i7. No, I'll say i5 only. HDD I'll say 1024 GB. HDD I'll say 256 GB, and this I'll say NVIDIA. And then when I hit on predict price, let's see what it is predicting. Yep, it's predicting almost like 68 to 70,000. Because of all these additional features which I gave, it is predicting almost that. 8 GB RAM, 256 SSD, 1024 HDD. SSD price is giving a lot of variation in this. Let's see that if I change my SSD to 128, what happens. See, just saw the result. If I change my SSD to 128 GB, it just dropped almost like 10,000 rupees. So you can understand how important this SSD feature is, right? Even if I change the I'll say even if I change my RAM to be 16, and let's say that I change from i5 to i7, and let me execute this. I think so this will be very more. Yeah, see, it is giving me correct result, almost like 75,000 to 77,000, and that is correct actually, because if you are having 16 GB RAM and 128 SSD and i7, then that is for sure gonna be more price. Let me take it as 256 in SSD. Now this is a fully loaded laptop. Let me see what happens. Yeah, so the price of SSD didn't affect that much, because already we are having some very good amazing features like 16 GB RAM, 1024 GB HDD, and i7 processor. So it just added a little bit to it, not that much. So it's lying between 79,000 to 81,000. Let me say that I will use this gaming laptop. So this just went very high, almost like 96,000 it went. So this is working absolutely fine. I think there is no kind of error, and this is not kind of being even biased. And I think if you just browse on Amazon or Flipkart, you will get this price range only, almost similar kind of price range only we will get. So this is how this Streamlit application is working. It's working really amazing. I mean, everything is so perfectly everything is so perfectly pre-processed and done, and it is giving a very good result as per the training of it is concerned. So in the next video we'll see about the deployment of this on Heroku Cloud, and till then, do practice this code. Hi. So in the last video we saw how we can integrate our pickle files with the help of the Streamlit application, where Streamlit is used to build the UI. Now in this video we will try to deploy our whole code into production using the Heroku Cloud service. So over here what we will do is we will import these dependencies, means this all is present, right? So we will try to deploy this code on Heroku Cloud. So for that we need an Heroku account. So for if you're having an Heroku account, just simply log in to go to heroku.com/login and then enter your email address and password, and then hit next. You'll log in. If you don't have any account at Heroku, you can sign up using the sign up link. Fill in your credentials. They will send a verification link at your email address, verify your email, and then you're all set. Then you can come back to this login page, fill in this credentials and hit login. So you'll be logged in. Then once you're logged in, you will see a page like this. We'll create a new app over here. Let's say that our app name is Lappy Price Predictor. See, they say that the Lappy Price Predictor is not available. So laptops prices predictor, let's keep it. I know it sounds kind of awkward, but still we have to do it, because there are no most of the people are using this free version and they will take the name first only. So we'll create an app. Okay, so now when the app is created, we'll be having three variations over here through which we can deploy our code. One is the command line interface, one is through GitHub, and one is to container registry. Okay, so now how we should use is we'll be using this Heroku command line interface. As I said, Streamlit applications, I use command line interface. Before that, we need to add these three files, that is proc file, requirements.txt file, and setup.sh file. So these three files are required. So in the proc file is like the main file of the Heroku app. It says that this is a web-based application where the setup of this whole application is written in setup.sh script. This is nothing but a shell script, and then this is a Streamlit app, so you have to install. So you go to the requirements.txt, install these two dependencies, come back here and run this code on your machine. So this is the proc file is the file which is the first file which gets executed when the Heroku service tries to run the code. Okay, so everything seems well and good. We have all our required code files. Now we will say Heroku login. We need to log in. So before that, if you just type in Heroku and just see Heroku, we see this kind of thing. Okay, then we will do Heroku login, and once we do Heroku login, we'll press any key except Q. So an automatic link would be opened here, and then it will ask me to log in, and I'm logged in now. It will show I'm logged in as this. Okay, now what I have to do is I will skip this line because I'm already in a directory. So I will copy this git init command, I'll paste it here, and I'll hit shift enter. So this will create a initialize an empty git repository. As we can see, this is a master branch. Okay, then we'll say git laptop price predictor, Heroku git remote a laptop price predictor, then hit enter. We see that this gets updated here. So now we will do git add dot once if we do git add dot then we will say git commit better. So yep, these all insertions are made, and then git push Heroku master, then enter it. So this is the final deployment code. So this is pushing all our requirements and all of the files which we have mentioned here onto Heroku cloud. So this will take a little bit of time. So yeah, it's installing all the dependencies and everything is working fine now. I think it's hardly 1 or 2 minutes it will take to finally push the application. So yep, that's almost done now. Deployment on Heroku will take a little bit of time if your application size is less, but if your application size is little bit more, it will take a little bit more time when you're having more kind of functions which are going on. So when you try to deploy a particular Django app, that time it will take a lot of time because Django requires a lot of updations which need to be done before deployment. So yep, so it's almost like 211.4 megabytes and it's launching, and this is deployed on Heroku, and we can hit on control click to this and we can see what kind of application this is. And there's one last step which is to be executed completely, and once it gets executed we'll see the end result. It's almost deployed, it's almost done, everything is working fine. Just one last statement, if it comes, it's confirmed, then we can just hit on this thing. So yeah, yep, so verifying deploying done, and master branch, and this is deployed successfully. So we can go to this page and this page loads Streamlit app. It's over here. We can change the configuration from here to settings, and then we can say theme, dark mode, and close, and we'll check if it's working fine or not. We'll say HP notebook, 8 GB RAM, Windows, weight of the laptop is 1.37 kilograms, touchscreen laptop, no touchscreen laptop, IPS, no, screen size is let's say 13.7 inches, resolution I'll keep it HD, Intel Core i5, HDDs 1 TB HD, so 1024 GB, and 256 SSD, and GPU is NVIDIA. Hit predict price of the laptop is predicted to be nearly 70,000 to 72,000 just because of this 256 SSD. I think if I keep it as 128, there will be a significant drop in the price. So this is working perfectly fine in production as well, and there are no errors or no bugs as such. And yep, this ends up the whole big project of laptop price predictor, starting from exploratory data analysis to the deployment of this application on Heroku Cloud. It just takes a few minutes in deployment, but exploratory data analysis takes a lot of time.